Okay guys, I wanted to do another video here. This one is going to be on vibrational spectroscopy, starting with diatoms. As we've discussed previously, infrared radiation is resonant with molecular vibrational transitions, and we use the harmonic oscillator model as the basis for our understanding and our interpretation of infrared spectra. The harmonic oscillator model is based upon the idea that for example, a diatom makes small oscillations, small displacements away from its equilibrium bond length. So R is the time-dependent bond length, and then RE is the average or equilibrium bond length of the diatom. And the quantity X represents the displacement of the molecule from equilibrium. So X can be positive or negative, and the idea of the harmonic oscillator model is that X is going to be small. When X is small, then you can make this approximation for the potential energy as a function of the displacement. You can treat it as a quadratic potential. This is the basis of Hooke's law, which you would have learned about in physics. And Kf is called the force constant. So essentially what we're doing is we're modeling the diatom as if it is connected by a spring, and Kf is the spring constant or the force constant. We can also write the force constant in a different way. We can write it in terms of the effective mass of the diatom, which in this case is also the reduced mass of the diatom. And then omega is the vibrational frequency. This would be the angular frequency expressed in radians per second. And so the quantity omega, you can set Kf equal to mass effective times omega squared, and then solve for omega, and you can get the frequency of the oscillator expressed as the square root of the force constant divided by the effective mass. And so this is an equation that's very commonly used in homework problems, and so we'll see an example of that in a second. One of the things you can do with infrared spectroscopy of small gas phase molecules is that you can use it to determine this force constant, which tells you something about how strong the bond is between the two atoms. Here is a visual representation of the potential energy for the harmonic oscillator. That's the black curve here, so it's a parabola centered at the equilibrium bond length, and then on the displacement scale that would be centered at 0. A true molecular potential energy function does something a little bit different. It looks like this. It goes through a minimum, but then rather than diverging, it converges to some value. So as you stretch the diatom very far apart, eventually the potential energy goes to 0, or whatever dissociation constant you're calling this, and you have the possibility of breaking the molecule, that is, breaking the bond. Whereas for the harmonic oscillator, it just keeps going up and up and up, and you can never break the harmonic oscillator bond. There'll always be a restoring force that brings it back. So certainly the harmonic oscillator model is realistic near the minimum of the potential, where the displacements from equilibrium are small. But if you stretch the molecule too far, clearly the harmonic oscillator model is going to break down. This diagram is meant to illustrate the effect of the force constant. So if you have a large force constant, that's going to give you a very tight parabola here, okay, corresponding to a strong bond. For a smaller value of Kf, you're going to have a looser bond, and the parabola will be wider. Well, we've looked at the harmonic oscillator before. Specifically, we've looked at the expressing the Hamiltonian for the harmonic oscillator problem, and then we've in fact already discussed the solutions to the Schrodinger equation for the harmonic oscillator problem. So I'm just reviewing the energy levels here that we'll need to understand infrared spectroscopy. So this is a formula that we've looked at previously. Here, the quantum number is the Greek letter upsilon. So upsilon ranges from 0 up to infinity. And this is the formula for calculating the energy levels. The key feature of the harmonic oscillator model is that the energy levels are equally spaced. And as we did with the rigid rotor energy levels in the last video, we're going to convert this formula from energy units to reciprocal centimeter units. And so that's all this conversion is here. We're just rewriting the energy as a wave number. And we're using the symbol G for the vibrational term, and it gets a little tilde to let us know that it's in reciprocal centimeters. But the formula is the same. What we've got going on here with this new tilde, this is now the vibrational frequency in units of wave numbers, and you can calculate it in terms of the force constant and the effective mass, just as you can for omega. Okay, so this is what we'll work with when talking about infrared spectra. Here, this problem, as I said before, standard physical chemistry problems involve working with this formula to calculate the vibrational frequency. So here we're considering hydrogen chloride. We're told that the force constant is 516 newtons per meter, and that's a very typical unit for diatoms. You should expect the force constant to be several hundred newtons per meter. Here the effective mass is calculated for us already, and they simply want us to calculate the vibrational frequency in units of hertz and reciprocal centimeters. So here I'm taking the force constant, divide it by the effective mass, take the square root. That gives you the frequency, the angular frequency in units of hertz. And then to convert from frequency to wave number, you need to divide by 2 pi times the speed of light. And then one of the tricks is to use the speed of light in centimeters per second, and that'll get you the wave number in reciprocal centimeters. So in this case, you get roughly 3,000 reciprocal centimeters. Okay, selection rules are important in spectroscopy, and if you calculate the transition dipole moment for different possible spectroscopic transitions involving the harmonic oscillator model, what you find is the gross selection rule that the electric dipole moment of the molecule must change during the vibration. And for heteronuclear diatoms, that's certainly true. As you stretch a heteronuclear diatom, the dipole moment of the molecule will change through the course of that vibration. However, for a homonuclear diatom, the dipole moment will be unchanged by the stretch of the bond. And therefore, homonuclear diatoms do not absorb infrared radiation, and we say that they are IR inactive. But heteronuclear diatoms are IR active. The specific selection rule involving the quantum numbers is given here. The quantum number upsilon must change by plus or minus 1. So when you're absorbing infrared radiation, you can only go up or down by 1 quanta of vibrational energy at a time. Here what we're doing is we're calculating the energy difference, or I should say the wave number difference between 2 adjacent terms. Okay, so if you're going to have a transition from quantum state upsilon to state upsilon plus 1, what would be the frequency difference between them? Well, what we find is that the frequency difference is independent of the quantum number. So all vibrational transitions have the same frequency. And that's a characteristic of the harmonic oscillator model because it has equally spaced energy levels. What kinds of transitions should we expect in the spectrum? Well, we need to consider the Boltzmann distribution. That is, what are the populations of the different energy levels at thermal energy? And so if thermal energy is around 200 wave numbers, what should we expect for the populations? Well, as we saw in the previous example, the vibrational frequency for hydrogen chloride is around 3,000 reciprocal centimeters. And so what's typical is that most molecules, the spacing between their vibrational energy levels is much greater than, by about an order of magnitude, greater than the thermal energy. And as a consequence of that, most molecules will be in their ground vibrational state at ordinary temperatures. So you really only need to worry about this fundamental transition from the ground vibrational state to the first excited state. For most molecules, this is all you're going to see. For some molecules that have low-lying excited states, excited vibrational states, you might see transitions from 1 to 2 as well, especially if the temperature is high. But generally speaking, you're only going to see this fundamental. We also need to take into account the fact that real molecules are not perfect harmonic oscillators, as we saw in the previous figure involving the potential energy. In fact, the energy levels, the vibrational energy levels for a diatom are not equally spaced. They get closer together as the energy increases. Moreover, the harmonic oscillator has an infinite number of energy levels, and real diatoms have a finite number of vibrational energy levels. And I mentioned this earlier, the harmonic oscillator model, the bond can never be broken. However, for a real molecule, the bond, if you put enough vibrational energy into it, it will dissociate. And so these are some facts that we need to contend with. One way of doing that is to adopt a different potential energy function. A commonly used one is called the Morse potential model. Okay, and you see that it's a more complicated function. However, it does give qualitatively the correct potential energy curve for a diatom. It features a couple of parameters. It features a well depth parameter, and it also features a shape parameter here that affects the width of the well. Let me turn to the picture here, just so you can see it. So this is a plot of the Morse oscillator, and it's illustrating this is the well depth parameter. So it's the difference in energy between the bottom of the potential energy curve and this dissociation limit here. So as you go out to large displacements, the Morse oscillator converges to some value, and the parameter dE controls the difference in energy here. The other parameter, A, controls the width of the well, and therefore, like you would expect, it's related to the vibrational frequency of the oscillator. And so you have this relationship as well that you can use. The dissociation energy here is expressed as, in units of wave numbers, it's expressed as the difference in energy between the dissociation limit and the 0-point energy of the harmonic oscillator. Remember that harmonic oscillators, the lowest quantum number, epsilon equals 0, has a non-zero energy called the 0-point energy. And so in order to dissociate the molecule, this D0 parameter represents the amount of energy that you need to put into the molecule in order to break the bond. Well, I think I covered everything I wanted on that slide. Here what we're putting together are the terms now for the Morse oscillator. So you would take the Morse oscillator, you would set up its Hamiltonian, you would solve for the eigenenergies of the Hamiltonian, and then to create the term here, you would take the difference between two Morse oscillator eigenfunction or eigenenergies, and that's what we have displayed here. You see that it has that same harmonic term, but then now it has an additional so-called anharmonic term, and this parameter xe is the anharmonicity constant, and it's expressed in terms of the other parameters of the model. and it's always a positive number. And so what you'll see, what happens here, as you increase the quantum number upsilon, you've got your harmonic energy level, but then this term subtracts from that. So what's going to happen is as upsilon gets large, this term is going to become larger and larger and larger, and eventually you're not going to have any more positive eigenenergies. And so there's a maximum value for upsilon. It looks like I used the wrong symbol here. This should be upsilon max. And here's a plot representing that. So you've got the Morse oscillator potential function, and then you have these different eigenenergies. And as you go to higher and higher quantum number, you see that the levels get closer and closer together, and eventually there is a maximum value that you can reach. And beyond that, you're in the so-called dissociation limit, where the eigenenergies then become continuous, and you have two separated atoms. This is a similar but slightly different way, slightly more general way of representing the anharmonic parts of the term. So you've got the harmonic oscillator part, you've got the part that the Morse oscillator gives you, but then you can generalize that and have a whole series of anharmonic correction factors, and then you can just include as many as you need in order to make your calculations more accurate. And so we're interested in the spectroscopy of this anharmonic series. And so we are going to look at the difference between adjacent terms. So a transition from upsilon to upsilon plus 1. So we take this expression, substitute in upsilon plus 1, and then subtract from that this expression itself, and you'll get a series that looks like this. So here's the harmonic term, right? Without this anharmonicity, we would simply have that all transitions have the same vibrational frequency. That's the result for the harmonic oscillator. But a consequence of anharmonicity is that you will have correction factors here that are going to modify that frequency. So the transition frequency from upsilon 0 to upsilon 1 is different from the transition frequency from upsilon 1 to upsilon 2, as you would expect intuitively from the plot. Another consequence of anharmonicity is that the selection rules are weakened. And so while for the harmonic oscillator, the quantum number must change by only plus or minus 1, for the anharmonic oscillator, the quantum number can change by more than just one quanta. And so you can have what are called overtones in the spectrum. So for example, going from quantum number upsilon to upsilon plus some value n, where n is greater than 1. And you can work out from the terms, you can work out what those transitions would be. By far the most important ones are the overtones from the ground vibrational state, since it has the largest population, to higher excited states. So n would be 2, 3, 4, etc. And this would be the formula that you would use to calculate those transition frequencies. And that's what's done in this. This problem is a little different. We're taking observed transitions. So we have the fundamental transition occurring. Let's see, that would be the 773.8. And then the first overtone transition for chlorine fluoride is at 1535. They want us to use these two numbers to estimate the anharmonicity parameter. So the first transition, the fundamental transition, has this form, and it equals that value. Okay, and then the second, the overtone, the first overtone, then has this term. So these results here are coming from these formulas. Okay, so you can just use this one. So you could plug in 1 and plug in 2, and that will give you the two formulas that you see here. And so we now have 2 equations and 2 unknowns, so you can solve for the fundamental vibrational frequency, and then you can solve for Xe, the anharmonicity constant. A Bird-Spooner plot is another thing that you can use when you have good data on the overtones. Successive terms. So if you take these different terms that we've calculated, okay, let's look at the form again. Okay, so we have transitions between upsilon and upsilon plus 1. So if you can observe these transitions and calculate these terms for different values of upsilon, and if you add all of those together, the sum of them add up to the dissociation energy. So in principle, you can directly measure the dissociation energy from the infrared absorption spectrum. And here's how that works. Here's a illustration of the plot. So the first term gives you the energy difference here. The second one gives you that energy difference. The third one, the fourth one. So if you just add up all of the ones that you see in the spectrum, you're going to eventually get to the dissociation energy. And here's what you would do. You would be able to observe a few of them, but then it would be hard to resolve probably some of the higher energy ones. And so you make this Bird-Spooner plot, which is, it's just a linear plot, okay? And then you're going to have to extrapolate the straight line, and then you can just take the area of this triangle to estimate the dissociation energy. And that's what's going on in this plot. They give you some data here. You would fit the data to a straight line. Once you have the formula for the line, you can then do the simple linear integral to calculate the area, and that's going to be equal to the dissociation energy. Here it's expressed in reciprocal centimeters, and you can convert that to a proper energy, kilojoules per mole, and you find that the dissociation energy for this H2 plus cation is around 250 kilojoules per mole. Here we're going to look a little more detail at infrared spectroscopy. For the case where you're doing your spectroscopy on gas molecules and you have good resolution in your instrument, you can actually see rotational transitions that accompany the vibrations. So as it says here, high resolution infrared spectra of diatoms show simultaneous vibrational and rotational transitions. And this is essentially the basis of the HCl DCl lab report that you guys are going to write. So this information here is highly pertinent to the lab portion of the course. So as the molecule is excited vibrationally, the molecule can also increase its rotational energy, or it can decrease its rotational energy. So you can have changes in the rotational quantum number that accompany the change in the vibrational quantum number. And so we're going to combine, it's a little counterintuitive, we're going to combine the harmonic oscillator model with the rigid rotor model. And so we're going to have a term here for our rovibrational spectroscopy that is the combination of the harmonic oscillator term, G, and the rigid rotor term, F, that we looked at in the previous video. Okay, so we're just adding them together. And so this term depends on the two quantum numbers, the vibrational quantum number and the rotational quantum number. And using our selection rules from rotational spectroscopy, the change in the quantum number J must be plus or minus 1. And depending on the type of molecule you have, you could also have the change in J could be 0 as well. But we're going to focus on this one. Okay. So what we'll see, and I'm just going to pull up the example here. So this is your lab report actually. So this is very much what your data looks like. So this is the row vibrational spectrum of hydrogen chloride, and what we're going to discuss are the different branches that you see in the spectrum. So there's a midpoint called the Q branch, which has no peak at it, at least in this spectrum here. And then there's a branch at lower frequencies or lower wave numbers called the P branch, and there's one at higher wave numbers called the R branch. And they have these kind of characteristic structures. And so here is the calculation of the observed frequencies. So the P branch involves a lowering of the rigid rotor's quantum number. So for the P branch, delta J equals -1. And we find that the peaks occur at wave numbers that are less than the vibrational frequency of the harmonic oscillator. So we take the difference of two terms. So notice that the quantum number for the harmonic oscillator increases by 1, but the quantum number for the rigid rotor decreases by 1. Okay, and so this is the difference in energy between these two terms, and you get this expression here. Okay, and you see that it decreases from nu linearly with J. And the spacing between the observed frequencies is going to be 2 times the rotational constant. So you get this progression of peaks separated by 2 times the rotational constant in the P branch. So the different peaks correspond to different values of J. So you plug in J equals 1. Actually, this should be, it should not start at J equals 1. It should start at, no, it can start at J equals 1 because there's a J equals 0. So it would be a 1 to 0 transition, a 2 to 1 transition, a 3 to 1 transition, etc. The Q branch corresponds to the case where delta J equals 0. Normally, for most molecules, that will be forbidden, but for certain molecules, it's not forbidden. In any case, if the quantum number J doesn't change, then the difference between the two row vibrational terms is just the vibrational frequency. And so the missing peak here corresponds to the vibrational frequency of the diatom. The R branch involves an increase in the rotational quantum number, so delta J is +1. And if we calculate the observed frequencies, you take the difference between the term involving upsilon and J, the vibrational quantum number increases by 1, and the rotational quantum number increases by 1. And here you find that the peaks have this, let's see, I think I may have a typo in the formula. I'm pretty sure that should be a plus sign. And I'm just going to check really quick. Yes, so I have a typo here, a big one. This should be a plus sign, so it should be nu plus 2b J plus 1. That would cause the wave numbers to get larger as J increases. And so these would correspond to transitions between J equals 0 and J equals 1, J equals 1 and J equals 2, 3 and 4, etc. And as you see here, the frequencies for those transitions just get larger and larger. Let's see here. I just wanted to comment on the intensity profiles that you see for the different peaks, and to remind you, if you think back to the microwave spectroscopy that we looked at previously, you'll recognize that form from the microwave spectrum, right? The microwave spectra also had these. Had this type of pattern. And the reason for that intensity pattern has to do with the populations of the rotational levels. And as we discussed in the last video, rotational energy levels, the spacing between them is very small compared to the thermal energy. So at ordinary room temperatures, most of the diatoms will be in their excited rotational state. And so that's why you get strong peaks for transitions involving the excited rotational energy levels. And that's explained here in this discussion, this caption. What can you do with this high resolution spectrum? Well, you can determine the molecular parameters. So you can use the location of the Q branch to determine the force constant for the vibrational for the bond in the diatom, and then you can use the spacing in the R and P branches to determine the rotational constant. And then, as we discussed in the microwave spectroscopy section, knowing the rotational constant allows you to calculate the moment of inertia, which in turn allows you to calculate the bond length. So you can use rovibrational spectroscopy to determine bond lengths and bond strengths of diatoms. Let's see, what are we doing here in this problem? They simply, in this problem, what they want us to do is to take the parameters for hydrogen bromide, and you would have to go look in the resources section to get the extended table that would have the entry for hydrogen bromide. Take those parameters, take the rotational parameter, and then use that to calculate one of the R branch transitions. So here they want us to calculate the transition from J equals 2 to, let's see, J equals 3. And so that and I've got the same typo persists here, but then somehow I magically corrected it for this formula here. What you'll just get the frequency that it occurs at. Anharmonicity complicates matters a bit. So if you want to go beyond the harmonic oscillator model, you can. You would include things like anharmonicity. You could include things like centrifugal distortion. And what that's going to do is it's going to complicate the formulas for calculating these different spectra. I have a little typo here. This should be the R branch frequency. These formulas include the effect of anharmonicity in the sense that different vibrational levels will have different rotational constants. So, for example, if in an excited vibrational state, the average bond length would be larger, and so the moment of inertia would be different, and the rotational constants would be different, and so that's taken into account in these expressions here. And what you find is that this effect causes the P branch lines, they're not perfectly equally spaced. They get closer together as the quantum number increases. You find that the R branch lines will get further apart as J increases. You can use tricks, basically numerical tricks, involving the so-called combination differences to take these equations, and by choosing carefully which value of J you plug into the different equations, you can isolate the different rotational constants. So basically you have two equations and there's two unknowns, and so you can solve for the two unknowns. You use to determine B0 here, you use two transitions, one in the R branch, one in the P branch, that involve the same upper state to determine B1, you would use two lines, one in the R branch, one in the P branch, that have the same lower state, and that's illustrated here in this picture. So you've got P and R branch lines. In order to figure out what the rotational constants are, you carefully choose two transitions that have the same upper level and two transitions that have the same lower level. I noticed previously that the figure is mislabeled. That is, this one should be called new P, and this one should be called new R. So if you spend some time thinking about this figure, just note that those are mislabeled. But anyway, that's how this works. And here's an example problem where they give you some information on two different transitions, and by comparing the values, you can find B0 and B1. And they're pretty close. Okay, so it's not a huge difference between them, but again, in high resolution spectroscopy, you can distinguish these types of differences. I believe this last little section is on a complementary spectroscopy. So what we've just discussed was infrared absorption spectroscopy, but you can also have scattering processes that occur involving transitions in the infrared range. And so Raman spectroscopy can be applied to vibrational transitions, and it involves inelastic scattering. Your incident radiation is typically in the visible range, and then through the inelastic scattering interactions, the molecule will undergo transitions corresponding to vibrational transitions. The selection rules are totally different. As we discussed in the context of microwave spectroscopy, Raman spectroscopy involves the polarizability of the molecule, not the dipole moment. And so the rule here is that the polarizability of the molecule must change as the molecule vibrates. And you have the same specific selection rule for the quantum number of the oscillator, but the selection rule for the rigid rotor portion of the transitions is different. Here, delta J should change it should either be a change of 0 or a change of plus or minus 2. And this was the same selection rule that we had for microwave Raman spectroscopy. But now we're applying it to rotational vibrational spectroscopies. As a consequence of the change in the gross selection rule, we will have both heteronuclear and homonuclear diatoms are Raman active. So you can use vibrational Raman to study molecular oxygen, for example, or molecular nitrogen, whereas infrared absorption can only be applied to heteronuclear diatoms. Okay, so when you scatter visible light off of a diatom, you will get both the anti-Stokes and the Stokes frequencies. Okay, so either the molecule will take away some of the photon's energy, and it'll undergo a vibrational and rotational transition, or the molecule could possibly undergo a transition from a higher vibrational state to a lower vibrational state, and that's the anti-Stokes line. Because most molecules aren't in their excited vibrational state, these types of transition, these anti-Stokes transitions, are very, very weak. And so we are going to focus exclusively on the Stokes transitions. Just like the infrared absorption spectrum has different branches corresponding to rotational transitions, the vibrational Raman spectrum will also have branches, but they're slightly different because delta J is not plus or minus 1, delta J is plus or minus 2 and 0. And so we have the same Q branch that occurs at the same place, but the other branches aren't the R and P branches. They're called the O and S branches, which is kind of cute. But the structure, the appearance of the spectrum is basically the same, although the Q branch is not forbidden specifically. It will have a Q branch. And so you'll get spectra that look like this, and the interpretation is roughly the same as it is for the infrared absorption, right? You've got changes in the rotational energy levels, and that causes the observed frequencies to either be greater than or less than the center frequency, which in this case is the difference between the incident light and the other light there. Well, I think we'll cut off the video there.